Alright, let's continue with our algebra lectures. This last thing that we're going to end here with is a proposition which, when I first looked through it, I thought, oh, there's not too much that we need to talk about here, but there's actually quite a few details that we need to go through. So, here's what we're going to do. This proposition is going to include some definitions, but anyways. We have an equivalent condition for having a semidirect product here. So we have a semidirect product. G is the semidirect product of, that is immediately wrong, it's of H and N. By the way, the reason we use this symbol is because this is kind of like a direct product, which would just be X, but then you have this line here which gives you a triangle, which is like normality, and so N is normal and H in some sort of way, and in the next lecture I think we'll talk about that a little bit more. But anyways, G is equal to this direct semi-direct product if and only if there is a short exact sequence. So here we have 1 to N to G to H back to what? Got homomorphisms phi and psi here. So we have a short exact sequence and we have another map. A map S. And this map S will go from H to G. It's going to be a homomorphism. Is it going to be a homomorphism? Let me... Yeah. Maybe. I don't know. We won't worry about that now. But there is some S here such that psi composed with S is the identity map on H. And so here I think this might automatically mean that S has got to be a homomorphism. I'm pretty sure for the forward direction, when we define S, it's going to be a homomorphism for sure. And I'm sure in the reverse direction, we'll end up needing it to be homomorphism. But anyways, there certainly is a map such that this holds. S is called a section of the map psi. And a short exact sequence with a section is said to be split. So not every short exact sequence is split. We'll have examples of those later on, of short exact sequences where there does not exist a map going the other way such that this composition will yield the identity. But if there is a section, then it's going to be called split. So anyways, let's prove this. Now let's hear, for the forward direction I had to flesh out a bunch of details. So for this direction, suppose that it is the case that G is the semi-direct product of H with N. By isomorphism theorem 2, which we just proved, we have H mod H intersect N is isomorphic to H N mod N. By the way, in this proof, and this is going to be one of the things that's going to make this proof confusing, I'm going to be really messy when it comes to saying that groups are equal and saying that they're isomorphic. There's going to be times where I say that groups are equal when they're isomorphic. But we're not really going to worry about that. It's just something you sort of have to get used to. So anyways, we have this, and just one more quick thing. If we did have explicit isomorphisms for everything, then there'd just be way too many functions here. And it's just easier to understand what things look like. Like when two things are isomorphic, we're just writing them differently. So we really don't need to worry about adding in all these isomorphisms. Anyways, stop rambling. So this. We have this isomorphism. In the proof of iso theorem 2, we're going to have to remember how we got this bijection, because we're going to need to use it for this proof. So we constructed this bijection by starting with the bijection isomorphism. We constructed this isomorphism, which is obviously going to be bijective in particular, but there's more to it. By starting with the surjective map, surjective homomorphism J from H to Hn mod n, given by J of H is equal to Hn, i.e. J is pi of I, with I going from H to Hn, and pi going from Hn to Hn mod n. So I'm going to use I and pi a lot here, and it's just going to be identities and projections. Let's see here. How many times am I going to use it? I'll just leave it like this for now. Actually, you know what I'm going to do? I'm going to call this I. I'm going to call this... Well, yeah, I can't do this I sub H because you don't know where you're including H necessarily. But anyways, okay, so we have this. And this, the fact that we write J like this is something that we did in the isomorphism theorem too. So if you don't recall this, go back and refresh yourself on that. I don't want to go back and reprove that. But part of the second isomorphism theorem was we proved that this map gives us a homomorphism, and we proved that's surjective. Okay, so we then quotiented H by the kernel of J, which we proved was equal to H intersect N, to get the desired isomorphism. Okay, so that's what happened when we were talking about the general isomorphism theorem. But let's remember what our particular case is. We're considering the case where G is the semidirect product of H and N. So, since G is the semidirect product of H with N, we know that Hn is equal to G, and we know that H intersect N is the identity. And so J is a map from H to G mod N is an isomorphism. Because G is exactly Hn. And so we can just exchange that, and then for H here, in order to get our isomorphism, we need to mod out by the kernel of J. But the kernel of J is H intersect N, which is trivial. And when you quotient out by the identity element, nothing changes. And so when you take J and you quotient out by E, it stays the same. And so J itself happens to be an isomorphism. Okay, so this is important. Okay, so since 1 or rather I'm going to write then, and then I'm going to draw a picture which is going to kind of explain what's going on. So we've got 1 going to N, going to G, going to G mod N, going to 1. This is a short exact sequence because N is a normal subgroup of G. That's one of the first things that we did when we talked about short exact sequences. Of course, here, this I'm going to call it I, and this I'm going to call it pi, meaning this is inclusion and this is projection. Of course, this is bad notation because this conflicts with this, but we're going to leave it. But what we have now is we have this map here. We can go from J mod N to H by J inverse. And that's a well-defined map because J is an isomorphism, and so it has an isomorphic inverse. It has an inverse, which is an isomorphism. And then, of course, H, we can just map into 1 in the natural way. And so we have the desired short exact sequence if we let phi equal the identity, inclusion, I'm sorry. And then we let psi equal, well, here we want 1 NGH1. So we have 1 NGH1. And so what's psi going to be? Psi is going to be going through pi and then going through J inverse. So it's J inverse composed with pi, because remember, compositions of functions goes backwards. So this is really cool, I guess. But another thing to note here, so what else, does this actually work? Well, you need this to be surjective, and certainly this map is surjective since it's a composition of 2 surjective functions. Isomorphisms are in particular surjective. And then, of course, because this is an isomorphism, it's you're not going to pick up, if you're trying to look at the kernel of psi, then certainly it's going to be anything that gets sent to here, and anything in the kernel of pi is going to be in the kernel of psi, but then anything that's in here is also going to be in the kernel of psi. But here we don't add any new elements to the kernel. The kernel of G mod N is the identity because it's injective, because it's an isomorphism. And so this map has the same kernel as pi does. And because this is a short exact sequence, the kernel of pi is the image of I here, this inclusion map. And so the kernel of psi is the image of I. And so that confirms that this, if we take this shortcut here through psi, then this is a short exact sequence if we take this this alternative path here. Okay, so that's part of what we wanted. So we have that, and now we need a map H such that composing psi with H gives us the identity. No. Yeah, we need an S such that composing psi with S gives us the identity. And I hate to erase the statement before we prove the statement, but I'm going to have to because I don't have enough room here for everything. Okay, it's looking like I might not finish this theorem by the end of the video. I might just do one direction and then I'll leave the other direction for next time. Okay, so this is so we're almost done with this direction though. Let's see here. We now want map S from H to G such that psi of S is the identity on H. So let's see here. Possible candidates for S. Well, let's see here. We're going from H to G. H is a subgroup of G. Let's just try inclusion. Let S be inclusion. Okay, then what happens when we compose psi with S? J is equal to pi of I. If you'll remember that, let's see here, it looks like I erased it. But if you remember how we define J, J is pi of I. Right. And so, so if we look at J inverse, that's going to be the inverse of pi of I. Let's see here. So, okay, so I haven't reused I, it looks like. The only I I've reused is here. So I'm going to call this I prime, actually, if E equals I prime. And so then this I, remember this is inclusion from H to Hn. But let's remember what happened in this scenario. We have G as the semidirect product of H and N, so so I maps from H to G, which means that I in this scenario is actually precisely the map S. So then, psi of S, what is this map? Ooh, am I missing? Did I choose S correctly here? Oh! Right. Okay, yeah, no, this is good. So psi of S, this is J inverse of pi of S. Okay, but what's J inverse? J inverse is pi of I inverse. And then this composed with pi. What's S? Remember, S is I. So we have this. And so if you write this out, this is I inverse of pi inverse of pi of I. And so the pi's will cancel, the i's will cancel, And so all we're left with is the identity map in H. And so that's it. That's exactly the type of S that we wanted. Or yeah, that's exactly the S that we wanted, wherever I wrote it. S is inclusion there. Yeah, S is right here. And so of course, since it's inclusion, it's a group homomorphism. Yeah, because obviously. Okay. So if that is part of what we need for the statement, then that is satisfied. And I'm pretty sure it is, because this is a nice theorem, so we want everything here to be nice. So anyways, hence 1 to n to g. Here this is I prime. This is to h, and this is psi. And this is 1 is split. And that's exactly what we wanted to have happen. And so that finishes this direction. And then all we have left is the reverse direction, and we'll be done.